So this is going to be slightly different than some of the other lectures. So I'm going to just talk very briefly, maybe like 5-10 minutes, kind of a general introduction to some of the computational side of things. And then everything that I want you to do has been typed up in this document, which has been provided on the website. So there's going to be a contrast here. What I'm going to do is show everything.
What's up? Perfect. No, I mean, I trust. Did anybody else see this one?
Yeah.
Okay.
Thank you.
All right, no, you're scared there for a little bit. So what I'm going to do is go through how you would take effectively raw reads. We're going to start with clean reads, but I'm going to go over what you do with raw reads, all the way through variant calling and some basic filtering. And we're going to be using the command line for this. So this is going to be a contrast to what you're going to see this afternoon when Tiago is going to go through. He's going to talk about some other stuff in terms of a theoretical aspect, but actually giving a little bit of a lecture. And then he's going to take the exact same data set that you're going to work with this morning and then do it using the GUI interface running on what's called the Galaxy platform. But so you had a little bit of this yesterday, and most of you know this by now, but from the computational side of things, high-throughput sequencing is going to be ultimately about figuring out where things go and getting things in the right places to be able to draw whatever conclusions you want to draw from your data. So you've got these reads, you've got a bunch of them, there's various lengths, 100 base pair, 150 base pair, more depending on what platform you're using. And the question is, given your reference, and this reference can either be a reference genome or it can be a set of targets that you've designed for an exon capture, maybe from a transcriptome or something like that, where do they go, and can we place them there confidently? And given that we place these things there confidently, can we call variants from them and get something useful out of it? As you might expect, this approach is very error-prone, and some of this stuff, my guess is that you went over this yesterday, but error can be introduced at a bunch of different steps. And the first is going to be library preparation. This has to do with more molecular sources of error. So say, for example, if you're amplifying out the set of targets, you might have a variant that's or substitution that's introduced, an error, whatever, by a polymerase. And if that error persists and is amplified up a bunch, that's going to kind of persist throughout your library. So hopefully you have enough fragments in there that that's not necessarily a big issue. You, of course, get error introduced in sequencing. So the platform itself is error-prone. That's the Illumina platform or Pyro sequencing or whatever. PacBio is a really high error rate, whatever molecular platform you want to use to actually sequence this stuff. And what's kind of interesting about the error rate in and of itself with respect to sequencing is that each individual machine often has its own error profile. So that makes it somewhat difficult if you're more of the computational side of things and you want to actually simulate reads, maybe test out, say, assembly approaches or variant calling approaches and mapping approaches, because it's difficult to get kind of a catch-all set of reads that might be representative of a kind of global error rate across sequencing platforms. Error can be introduced in read cleaning, that is trimming off kind of crappy bases, trimming off adapter sequences. Definitely introduced in assembly. So Jeff mentioned this a little bit in passing. If you don't have a good reference, depending on your data set, you actually have to assemble things first. So genomic assembly can be very complicated. It can take a lot of time, a lot of memory. It's a very difficult issue. And placing things into genomic context, placing the reads themselves, can be this kind of week-long, month-long, year-long endeavor, depending on the size of your data set. So you don't say, hey, I'm a human, we're going to get some of my DNA, we're going to throw it in a tube and sequence it, and we're going to push a button and we're going to get all of our chromosomes out. It doesn't go that way. We're going to get tons of fragments, tons of scaffolds. We need to figure out exactly what's happening. So you might expect misassembly to be a source of error. Reads can be mapped to wrong locations. That is, where you're figuring out where they go. It's not always the case that there's always one best hit in the genome or in your reference that you've assembled. So errors can be introduced there. You can have errors introduced in post-mapping processing, things that we talked about briefly yesterday as well, I think, things like indel realignment. Calling indels is a little bit tricky. With genomic scale data, that is insertions and deletions, and finding the appropriate place at which to insert those gaps is computationally challenging. Variant calling, of course, we went over that yesterday for sure. And then there can also be errors in post-processing. That is, what you do with the variants once you have them. How do you filter out bad variants? How do you keep good variants? Can you think of it that way? And if you have really good sets of variants in a really well-validated model system, like humans, for example, you can do certain steps that will specifically correct for this. It's called variant quality score recalibration. And it's a way to say, hey, I know there's a SNP here. Let's go ahead and give it a second pass and see what happens and make sure that that's actually a really good call. So I don't know if this was described much at all yesterday, but one of the ways in which you call SNPs is by looking at the alignment itself, so how you actually do the mapping. So if your reference is up here, so it's a token example, each one of these little bars is reads, and then you've got some polymorphisms in here relative to the reference in and of itself. They can either be matches with the genome, in that case everything looks pretty clean. There can be real mismatches, and those mismatches can either be sources of error or true variants in the data set. So the way in which the probability of actually calling a variant is calculated has to do not only with the base call to reference genome, but then the actual base through all the reads, depending on your coverage. So that's how you get good variance. That's how you get good quality scores up good variance. So it's the probability of having a variant is going to be a function of the probability, or the function of the base call to reference genome plus the other bases in the reads at that position. So the goal of this kind of workshop, there's a couple goals. The first is just to introduce a very general workflow for data analysis. And this workflow is going to encompass what you do going all the way from raw reads to variants. We're going to focus on this in an exon capture framework. I'm going to describe the data structures of the common files, that is what these files actually look like, BCF. I guess you went over FastQ yesterday, BAMs, that sort of thing. And I want to make sure that you perform analyses using Unix command line. Again, this is going to be in contrast to some of the stuff we do this afternoon, but I think it's really important. And that's because if you know how to use everything using the command line and run these approaches, it's very easy to scale up from, say, going from 10 individuals, 20 individuals, all the way up to 1,000. And it allows you to manage the computational side of things, that is, your CPUs and your memory, in a much more efficient fashion. So Tiago's going to analyze the same data set using Galaxy. I already talked about that. And I really want you to ask me about any problems you might be having with your own data sets and what other type of analyses you might want to perform. So how many people are interested in performing molecular evolutionary analyses of data? Things like looking at selection and evolution stuff. Yeah, so general. How many want to do phylogenetic approaches, or things that maybe use trees like comparative phylogenetic methods? Okay. So it's not always the case that you'll be able to get your reads and then run everything through the variants and then throw it straight into these analyses. So phylogenetics, for example, you might not want to have the SNPs in and of themselves. You might actually want to have, say, the whole target that you captured. And that's because you might want to do model-based phylogenetics or those sorts of analyses that are relevant. The exact same thing applies to selection analyses. So if this is something that you're interested in, come and talk to me, come and talk to Jeff or Tiago. We can break it down for you and hopefully give you some advice on how to analyze this data. So something that's recommended I talk about briefly is what skill set you ought to develop if you're going to be interested in doing more programming and doing a lot of high throughput sequencing analysis. So my recommendation is that you get very comfortable with a Unix environment. There can be any flavors of that. Plus a shell language. Now, I recommend Bash. There are other shell languages. Most people in here probably know most familiar with Bash. And that's kind of a good starting point. So that allows you to do things like not only execute the commands you want or execute them within loops or in a parallel fashion, but also look at what's going on at the system at any given time. And that includes things like memory utilization. Are you running your system out of memory? How many CPUs do you have? Then I take this particular analysis. Maybe instead of running it on one CPU and it takes a day, I can give it to 10 and it takes an hour. So these sorts of things come into play when you really have these huge data sets. I also recommend learning a scripting language. I do a ton of R and a ton of Python. Perl was really popular back in the day and is still popular now. I would argue that Python is catching up. In some cases has better libraries that you can work with. That is pre-established packages that you can use for your data analysis. And if anyone in here is really interested in application development and is coming up with your own sets of approaches, learning a compiled language like C, C++ is a really good way to make a program, get it distributed to a bunch of people that can use it on different computers. So that's what's called being portable. And C and C++ are very memory efficient and often run faster than some of the scripting languages. And there's lots of help available in a bunch of communities online. So once you learn the basics, you can go in and search online and actually ask questions to a bunch of the world's experts who participate very regularly on some pretty big user groups online. So Stack Overflow for computational things, a bunch of programming languages, a bunch of stuff about system administration, Unix, Linux, all that sort of stuff. I contribute pretty regularly to BioStars and SeqAnswers, so if people have questions about bioinformatic analyses or things are getting kind of weird with their analysis and they're not sure what to do or how they maybe ought to do some analyses, tons of users on here every day, and they really want to help people out, including individuals that have developed their own applications and make sure that people use it. So you can Google online, there's lots of great options. So just a little bit about the exercise you're going to be doing here in a couple minutes. I've structured the document that I sent out so that there's a little bit of background material, and then every command you're going to run, I kind of explain what's going on behind the scenes. So there's going to be all sorts of information. You shouldn't need to necessarily go online and figure things out or look at manuals or anything like that, although you're more than welcome to if you want to learn what additional options might be available. And we're going to be starting from clean reads. So you get your reads off the machine. Let's assume that they've already been split up by barcode, just talked a little bit about yesterday. But taking raw reads and throwing them straight into analysis might not be the best way to go. You might want to do some pre-processing and cleaning. That includes things like adaptive trimming and debugging, and quality score kind of tools on those reads. But that takes a while, so we're not going to do it. So the data files that I've given you to start off with are clean reads. And then, depending on how things go, I'm going to stop periodically and then show a little bit about the data structures. These big files, they're a bunch of gigabytes. They take up a lot of memory when you execute them, and a lot of hard drive space. And they look scary, but they're not that scary. In fact, they're very good data structures and pretty efficient with respect to being read by programs and even being read by humans, given that you know how to scale. So the data set we're going to be working with today is a real data set, and it was a mouse exome capture experiment. This is for Muscardus, it's the Algerian mouse. The original capture is 55 megabases, so 55 million base pairs, and the mouse genome is about 2.8 gigabase pairs, so just shy of 3. One benefit of using a really well-established reference genome, like mouse, like human, is that we're kind of spoiled. So I worked in a lot of systems that don't have reference genomes, and as a result, you're not able to take that next step, and that is get really well annotated sequences. And by annotations, I mean things like saying this position is a 0 or 4-fold degenerate site, this position is protein coding, this position is regulatory. This is an exon that belongs to this particular gene. So given that we have all of this information, it makes sense that we can really use a reference genome, go back, map to that reference genome, and then we get all that information as well. So that's for really well-established model systems. But analyzing all this information at once is going to take too long for this workshop. So in place of the whole genome, I selected a 20 million base pair region of chromosome 1. And there are about 50 transcripts that are contained within this region, and I'm defining a transcript here as just saying the first exon starts within that region. So there's going to be more transcripts, but 50 genes or so. So I briefly mentioned pre-processing reads, and again, you're not doing this, but what you might expect to do when you pre-process reads, the very first thing is to remove low-quality base calls. So there's a couple ways in which a raw read can be processed down. Often at the ends of the reads, the base quality scores that I think were introduced yesterday are lower, and that means the probability of error at those bases is actually higher. So what several applications do, several algorithms will do, is start at one end of the read and begin to trim off these kind of crappy, low quality bases until the average quality of the entire read is above some threshold. Once that's done, often the next step includes something like removing residual adapter sequences. So adapters are these things that have to be tacked onto the reads. So you prepare your library, you fragment it, you tap these adapters on, and then you do some other stuff and you send it off for sequencing. Well, if your insert size of your reads is less than the sequencing, less than the size of the sequencing, so say you have, say a certain subset of your reads, maybe something went super wrong, and it's been fragmented down to 50 base pairs, and yet you're sequencing it on a platform that has 100 base pairs, reads that are being generated. What you can do is start at one end of the read, and you actually sequence through, and so you start getting additional adapter sequence. So it's this kind of chimeric sequence where you've got the stuff that you really want, but then you have all these additional sequences that you don't want. And you might imagine a circumstance where if this were not dealt with, either by a mapper or by removing adapters at the beginning, that you would align your read to a reference genome, so you have all the bases you want, and then you have your reference genome with all this adapter sequences, and it might be the case that those are actually called as variants. So it's just to find a way of going through and cleaning up the reads and making your data a little bit nicer. It also improves computational speed. And then another step that I really like to do is to merge reads that overlap. So if you have a forward and reverse read, and the insert size gets kind of small, you can actually combine the reads and treat them as a single read. This again increases computational efficiency. Okay, so that's kind of general introduction. So you talked about FastCompiles briefly yesterday, but again, there's 4 lines. You have kind of a description line, the actual base calls, a plus sign, and then the quality scores. These are ASCII quality scores. This is going to be the starting point for the analysis in the workshop. So go ahead, go through, start skimming through the document. We'll start with a FastCompile that's been cleaned, and map it, and go through a series of steps that we use to go all the way from mapping and then through and some subsequent. So I'm going to walk around, see if you have any questions, if anyone has any concerns. Let me know if one of the commands doesn't work. It might be the case that something has changed in the interim, and I'm more than happy to figure that out. And then I'll stop every now and then. I'm going to go over the SAM format and the variant call format.